Welcome to another video of quantum field theory, and today we'll be continuing from the last video and we'll be learning about the number operator. So let's begin. So the number operator is just some operator that acts on some state vector and gives us the number of particles in that system times the state vector. And this is going to be the form for the number operator. Now you guys may be asking, how do we know that's the number operator? How do we know that's the form that tells us the number of particles in our system? The answer is through using this operator, we will be able to see why in practice we call it the number operator. But for now, let's just assume that this equation, this fancy equation, is actually going to be the number operator. So the question then becomes, if we have some A conjugate K number that acts on the vacuum state, it gives us a new state. How many particles are in that new state? How many particles? Well, in our last video, we already learned that this state is just a state that has momentum K. But how do we know that it's not 2 particles or 5 particles that all add up together to have momentum K? How do you actually know how many particles are in that state? So this is where the number operator comes in. To know how many particles are in the state, all we have to do is multiply it by the number operator. And it should give us some scalar times the input. And the scalar n will be the number of particles in our system. So let's actually just do that, right? So let's take this number operator over here. Let's copy that. Let's paste it here. Okay, so n acting on A conjugate K, acting on the vacuum state, it's going to be equal to this over here. So we added parentheses here so that you guys can see where we're actually plugging it in, but we don't actually need to have those parentheses there. So now we can actually notice this term in the green, and we can expand this term out by referring back to our commutators. So that's just going to be this term right over here. And we can just expand it like this. And we derive this with our commutator relations. So this term is just going to be expanded out as 2 pi cubed delta of k prime minus k plus A conjugate k A of k prime. And then we just have to multiply it. Oops, you have to put another parentheses there. Then we just have to multiply it by this over here. And then, of course, integrate over the momentum. So let's move this a bit down here. Let's actually make it a bit larger. It's kind of hard to see it right now. So that gives us that expression. So now we have this expression for the number operator. What we can do now is we can just distribute this vacuum state on the inside. And we know that once the vacuum state acts on this term over here, we're going to get 0, since A of k prime acting on the vacuum state gives us 0. So that's just going to give us. So now we have this over here. And these 2 pi cubes are going to conveniently cancel out. And we can use the property of the delta function, where the integral of f of x times delta of x minus a is just going to be f of a. So that's just going to leave us out with A conjugate k times the vacuum state. So in short, n acting on A conjugate k acting on the vacuum state just gives us A conjugate K acting on the vacuum state. So it just scales it by a factor of 1. It gives us the exact same thing, which implies that our eigenvalue is just 1, meaning that in the state A conjugate K acting on the vacuum state, there is 1 particle. And we saw in the last video that it has a momentum of K. So the number operator so far seems to actually be working, but what happens if we have A conjugate K acting on the vacuum state? What state does that give us? How many particles are in that state? Again, what we do is use the number operator, and we just act a conjugate K times the vacuum state onto the number operator, and we just see what we get as an output. So here, you guys can see where we plugged in that double A conjugate K. What we can do now is the same thing as before. We can revert back to our commutation relations above here. So let's just copy that and paste it for convenience. And we can see that we have this exact same term right over here. So we just have to expand this term in terms of this. And that's going to give us so we now get this over here by just plugging in our commutators. And by the way, since we ran out of space, this entire thing is being multiplied by A conjugate K. So what we can do now to make this expression a bit more nicer to look at is we can just distribute our A conjugate K inside this term. And that's going to give us all multiplied by the vacuum state. So this is a bit more nicer to see. Let's just erase this to make some more space, and then move this up. So we can again see something pretty familiar. We again have this A of K prime, A conjugate K term, which is exactly this over here. So again, we can just use those commutation relations, and by doing that, we are going to get. So now what we can do is we can actually have to notice that we are multiplying all of this by the vacuum state, right? So we technically have to add another bracket right over here. It's getting pretty messy, but it's going to be less messy once we distribute our vacuum state on the inside. And doing that, we know that this term is going to go to 0 since A of K prime acting on the vacuum state gives us back 0. So that's going to give us. So now we have this term right over here. So what we can do now is we can just distribute the delta function times 2 pi cubed out, and that gives us. And we can notice that we have the exact same term twice, and that's just going to give us 2 times the same term. So times 2A conjugate K acting on the vacuum state. We can then just use the property again about the delta function. These cancel out, and this is just going to give us 2 times A conjugate K acting on the vacuum state. So again, we had n of A conjugate K acting on the vacuum state gives us n times A conjugate K acting on the vacuum state, and n is just going to be 2. This means that A conjugate K acting on the vacuum state gives us some state that has 2 particles inside. So this is a pretty interesting thing here because A conjugate K, well, let's use a ladder here. So the vacuum state has 0 particles, right? And we can just put this into the number operator to confirm that it has 0 particles. A conjugate K, acting on the vacuum state, gives us a state that has 1 particle. And then A conjugate K, acting on the vacuum state, gives us a state that has 2 particles. Now note that this state was just a particle state that had 1 particle with momentum K. So this state is just going to be A conjugate K acting on that 1 particle state. And that gives us, again, 2 particles. And so it gives us 2 particles. What's the momentum of that state? Well, remember that the momentum operator is the integral over the momentum times A conjugate K prime A conjugate K. So the momentum operator is literally just the number operator scaled by a factor of K, right? So this means that the momentum operator acting on A conjugate K, acting on the state that has 1 particle with momentum K, which I'll just call the first particle momentum state, that's just going to give us where n is the number operator. So that's just going to give us 2, so you get 2ki. So not only does this state over here have 2 particles, but the total momentum of the state is 2 times ki, which was the momentum of the state with 1 particles. So it gives us 2 particles that each have a momenta of ki. So the combined momenta is just 2ki. This tells us a very profound property of this A conjugate K. A conjugate K will act on the vacuum state and give us a state that has 1 particle with momenta K. If we repeat that again, it gives us 2 particles of momenta K. If you repeat it again, A conjugate K, A conjugate K, A conjugate K on the vacuum state, we have 3 particles of momenta K. So A conjugate K just creates another particle. It just adds another particle in our system. And because of this, physicists like to be a bit dramatic, and they call A conjugate K the creation operator, since it creates more particles in our system. So yeah, that's a really cool property of A conjugate K. And not only does it create new particles, but it creates identical particles. And we call these particles identical because it's giving us another particle that has the exact same properties as the previous particle, right? They have the exact same momenta, so we'll see that they have the exact same energy, the exact same mass. They could have, once you get to spinors, right, the Pauli exclusion principle, we'll start to see some differences there. But these are going to give us identical particle states. So now the new question is pretty much, when A of K acts on some state, let's say A of K is acting on, just say that has 1 particle of momentum K, what does that give us? Does it also add another particle? Does it add 2 particles? What does it do? Well, again, we do the same procedure here. We take the number operator, right, and we basically have to expand out A of K acting on the first particle momentum state. That gives us this over here, right? And just expanding things out, right? I encourage you guys to try this out yourself, but just use this to like check your work. So we just expand it out, right? We use the fact that we have this commutator In this case, we have A of k prime times A of k instead of A of k prime times A conjugate k. So we can still use the exact same commutator as before. Well, not the exact same one, a bit of a different one. That's also in second quantization. Doing that, we can expand it like this over here. We can cancel some things out. I also color-coded this for you guys so that it makes more sense. So everything is color coded. So this A of k, A conjugate k, and the blue is equal to this right over here, I think, maybe. So we continue on, things cancel out, which is good. We have to use the commutator again. We can use the one for the first one. We can do some more expansions, multiply everything by the vacuum state. We cancel some more things out. Then we end up getting A conjugate k, A of k times 0 equals A of k, A conjugate k times the vacuum state, not 0, the vacuum state. And then, yeah. So the reason why we could do this is because A of k and A conjugate k equals A conjugate k, A of k. They actually commute for the same k, which was why we were allowed to shift them around. So that gives us 0. Then we use the number operator again, and we use that to declare that we have n equals 0 for A of k acting on the first particle momentum state, which basically tells us that A of k removed a particle from our state. We had one particle of momentum k, and A of k just destroyed that particle. It annihilated that particle. It moved it away, and now we just have the vacuum state. No particles in our system. And that's actually what makes us call A of k the annihilation operator, because it removes a particle from our system. So basically, A conjugate k acting on some state with n particles gives us a state with n plus 1 particles with momentum k. And then A of k acting on some state with n particles with momentum k actually is going to give us n minus 1 particles with momentum k. And this is what actually motivated A of k acting on the vacuum state equals 0. Because the vacuum state has 0 particles, so there isn't any particles left to destroy. So A of k acting on the vacuum state gives us 0. But this will technically be circular logic since we actually used that property to derive that. So it kind of comes full circle in a way. There is a better way to justify this property over here, which requires the Hamiltonian, which we'll be talking about in the next video. So what we've learned is that A conjugate k creates particles, then A of k destroys them. And we call this the creation operator, and we call this the annihilation operator. So there's an important thing to emphasize here. Say we had A conjugate k prime acting on the vacuum state. That's going to give us a particle state, one particle that's momentum k prime. See, we have A conjugate k acting on A conjugate k prime acting on the vacuum state. That's going to give us one particle with momentum k and another particle with momentum k prime. And we can do the math to sort of verify this, but using our intuition that we've developed from the first part of this video, we can kind of understand why this makes sense. Because since this creates a particle with momentum k, if this acts on some state that has one particle with k prime, it's going to add another particle but with k, since these are both k. If you had A conjugate k prime prime acting on some particle state that has one particle with k and one particle with k prime, that's going to give us one particle with k, one particle with k prime, and one particle with k prime prime. Analogous, it's analogous with the annihilation operator. The annihilation operator acting on, say, K, or of K, acting on some state that's like, say, 2 particles with K, and then 1 particle with K prime, that's going to give us 1 particle with K, 1 particle with K prime, since it removed 1 particle with momentum K from our system. So what's inside the parentheses does matter, since it kind of indicates which particle with which momentum we're adding or removing from our system. So the number operator works in a similar way. The number operator of K acting on, say, this state, that's going to give us 1 times 1K 2K prime, since there's 1 particle with momentum K. If we've had NK prime acting on this Fock state, we would have 2 times 1K 2K prime, since there are 2 particles with momentum K prime in our system. So number operator doesn't tell us the total number of particles in our system. Instead, it tells us the total number of particles with some particular momentum in our system. So it sort of picks out that in our system. So these creation and annihilation operators, they sort of like act as like ladder operators, right? They allow us to move throughout our Fock space. Because remember that our Fock space is just a space, the state space of like 1 particle with momentum K, and then 2 particles with momentum K, 1 particle with K, another particle with, say, K prime, and so on, and then linear combinations of those things. These operators allow us to sort of get to any Fock state that we want to. So they allow us to move along our Fock space. So, yeah. And I think that's pretty much it for today's video. So yeah, those are the creation and the annihilation operators. And that's how they work. So thanks for watching, and I'll see you guys in the next video. Bye.